Chapter 9, Salts and Aqueous Solutions. In this chapter, we will explore the nature of salts and how they interact with water. A quick recall from Chapter 4. Metals on the left side of the periodic table lose electrons to form positively charged cations, and nonmetals on the right side of the periodic table gain electrons to form negatively charged anions. When the average person thinks about salt, what usually comes to mind is table salt, sodium chloride. In the eyes of chemists, salts are broadly defined as ionic solids. A salt is formed when a cation from the left side of the periodic table combines with an anion from the right side of the table with no net charge. In the figure on the right, a potassium atom loses an electron to become a potassium cation, K+, and a fluorine atom gains an electron to become a fluoride anion, F-. Because opposite charges attract, these two ions come together to form a salt, potassium fluoride. Salts packed tightly into a crystalline lattice, like the one shown to the right. These ultra-strong ionic interactions within the crystalline lattice cause the salts typically to have an extremely high melting point. For instance, sodium chloride melts at 801 degrees Celsius and becomes a gas at 1413 degrees Celsius. Monatomic ions are ions with only one atom involved. These ions can be cations or anions. We have seen quite a lot of them, such as sodium ion, Na+, and chloride ion, Cl-. On the other hand, polyatomic ions are ions that consist of more than one atom. For example, nitrate ion, NO3-, contains one nitrogen atom and three oxygen atoms. The atoms in a polyatomic ion are usually covalently bonded to one another, and therefore stay together as a single charged unit. Some polyatomic ions are given to you in table 9.1 to the right. Remember, salts are electrically neutral. This applies to the ionic compound containing polyatomic ions as well. Naming ionic compounds containing polyatomic ions. Rule number 1. The cation is written first in the name, followed by anions after. Rule number 2. When the formula unit contains two or more of the same polyatomic ion, that ion is written in parentheses with the subscript written outside the parentheses. For example, barium nitrate is Ba parentheses NO3 close parentheses 2. Barium is a +2 charge. Nitrate is a -1 charge. Therefore, you need to have two of the nitrate ions to balance the charge from barium. So therefore, you have to put a 2 as a subscript outside the parentheses. Please note parentheses and subscripts are not used unless more than one of a polyatomic ion is present in the formula unit. As an example, calcium sulfate is CaSO4, not CaSO4 parentheses. Rule number 3. If the anion is monatomic ion, the anion is named by adding the suffix IDE to the root of the element name. For example, ammonium sulfide is parentheses NH4 close parentheses 2 S. In this example, the polyatomic ion is the cation ammonium in the formula. Salts that absorb water are known as desiccants. When salt absorbs water, ions in the salt attract water. This is related to the properties of water we learned in Chapter 8. First, we know that water molecule is bent in shape. Second, because oxygen is more electronegative than hydrogen, in any bond between oxygen and hydrogen, the electrons are pulled toward the oxygen atom and away from the hydrogen atom. Last, because the oxygen atom is partially negative and the hydrogen atoms are partially positive, the water molecule is polar. A dipole of water molecule is drawn to your right. When ions attract water, they become hydrated. When an ion becomes hydrated, the ion is surrounded by water molecules. As illustrated below, the purple bar represents the positively charged sodium cation. It is attracted to the negative end of the water molecule. The water molecules packed in around the sodium ion as closely as possible. We say the sodium ion is a hydrated ion, an ion that is surrounded by water. This process is called hydration. The same attraction happens to the chloride ion. It is attracted to the positive end of the water's dipole, as shown to the right with a green color ball. These attractions between ions and polar molecules, such as water, are known as ion-dipole interactions. The ion-dipole interaction is another type of intermolecular force. It is stronger than the hydrogen bonding we learned in the last chapter. When water molecules and ions are combined, they mix well because they are both polar. We use the term aqueous solution to describe a uniform mixture of water molecules and another substance, such as a salt. Usually, when salt and water are combined, the salt dissolves in the water and does not remain in the solid phase. As each ion in the salt crystal becomes hydrated, the ions are plucked away and dispersed throughout the water. In this way, they dissolve to eventually make a clear solution, as shown in the picture below. In this aqueous solution, the substance that's present in the greater amount in a solution is called the solvent, in this case, water. The solute is the substance present in smaller quantity in a solution, in this case, is the sodium chloride salt. Salts dissolve well in water because water is polar, and salts are also polar. Whenever we are dealing with dissolving substance in a solution, we can apply this rule of thumb. Like dissolves like. It means that substances with similar polarities tend to dissolve easily in one another. So if something is ionic, like a salt, it will dissolve in a solvent that is polar, like water. In the same way, nonpolar substances tend to dissolve readily only in other nonpolar substances. Thus, a nonpolar substance like grease easily dissolves in another nonpolar substance like gasoline. The hydration of ions happens so readily that most salts dissolve easily in water. When a salt breaks up into its ions to become part of a solution, we refer to this event as dissociation of the salt. In the example below, we have potassium chloride salt dissociate to make one potassium ion and one chloride ion. The AQ notation on the right stands for aqueous solution. It means the salts are dissolved in water. In the second example, calcium fluoride dissociates to make one calcium ion and two fluoride ions, because each formula unit of calcium fluoride contains two fluoride ions. Water molecules hydrate ions. Most salts dissolve readily in water. In chemistry, we say that such salts are soluble in water or that their solubility in water is high. But there's always a limit to the solubility of any solid. If we have a lot of sodium chloride, but only a small amount of water, we run out of water before the hydration process is complete. The available water hydrates ions from the sodium chloride crystal one by one. Eventually, if enough sodium chloride is present, all the water molecules are used up in the process of hydration. When this happens, we end up with a pile of undissolved sodium chloride salt in the solution. At this point, all water molecules have absorbed as many ions as they can. No more sodium chloride can dissolve in it. We describe this as a saturated solution. In the saturated sodium chloride solution, we have a pile of salt sitting on the bottom of the solution, saturated with hydrated sodium ions and chloride ions. It may seem like nothing is happening in the solution, but this is not the case at the molecular level. Whenever the hydrated ion bumps into the solid sodium chloride crystal, the ion can shed its hydrating water molecules and return to the crystalline lattice. We refer to this return to the solid state as precipitation, a term that describes things that are falling, such as rain. In this case, the ions are falling out of solution and re-entering the solid phase. Now we have a few water molecules available to hydrate other ions from the salt. These reactions are going back and forth endlessly. When a saturated solution has been sitting long enough, there is no net change in the size of the salt pile, and we say the system is at equilibrium. Equilibrium is described as dynamic because the ions are still moving back and forth between the aqueous and solid phases. For a solution in dynamic equilibrium, the rate at which ion leaves the solid and go into the solution equals to the rate at which ions return to the solid lattice. Equilibria exist in many other situations. The surface of a liquid can be at equilibrium with gaseous molecules in the air above the liquid. Molecules of water in the solid phase, such as ice cubes, are at equilibrium with molecules of water in the liquid phase at the freezing point of water. Salts can suck water from anything they touch. Salts can wedge into knocks in sandstone monuments. They absorb water from the air and expand, pushing on the monument until it crumbles. When salts dissociate in water, they produce hydrated ions. The presence of ions means the solution can conduct an electric current. The beaker on the left contains pure water. The light bulb is dark because pure water cannot conduct electricity. The beaker on the right contains a solution of some salt dissolved in it. The bulb is lit because the salt dissolved in water yields a solution capable of conducting electricity. Both salts and the ions that form them are frequently referred to as electrolytes. We often hear about maintaining electrolyte balance in discussions about human health. The dissolved salts in the body are critical for maintaining blood pressure, neural function, and healthy cells. Sports drinks have a chemical makeup similar to that of a sweat. They replace the electrolytes and water loss during the physical exertion. Gatorade was developed in the 1960s at the University of Florida to help the football team stay hydrated during the practice in the Florida heat. If we want to understand how much of a given substance is present in a solution, we express that amount in the units of concentration. Concentration is the amount of one substance, the solute, dissolved in another substance, the solvent, in a solution. One of the most common ways to express concentration is molarity, which is the number of moles of solute per liter of solution. Chemists use capital letter M as a unit of concentration, which means moles per liter. We can express molarity by saying the molar concentration of a solution is 1 mole per liter, or the molar concentration of that solution is 1 molar. We can modify molarity with the prefixes in the same way we modify metric units. For instance, we can change molar to nanomolar or millimolar. Let's take a look at an example of molarity calculation. How many grams of table salt would have to be added to a 1 liter flask to make a 0.052 molar solution of sodium chloride? First, when you see the 0.052 m molar, you're going to convert it to 0.052 moles of NaCl per, meaning division, 1 liter of solution. This is simply by the definition of molarity, moles of solute per liter of solvent. Then you're going to simply multiply by the molar mass of sodium chloride, which is 58.5 grams of sodium chloride for every 1 mole of sodium chloride. After you punch it into a calculator, you will get 3 grams for answer. So you will need to add 3 grams of sodium chloride for every 1 liter of the solution to make the solution concentration as 0.052 molar. Keep in mind that the concentration of something in something else does not depend on the total amount we have. As shown in the picture below, this saltwater swimming pool has a molar concentration of salt equal to about 0.052 molar. If you take a beaker and fill it with the water from this pool, the molarity of water in the beaker is also 0.052 molar. Molarity does not depend on the volume of the sample. Can we use molarity for substances such as chocolate syrup that are already a mixture of substance? The answer is no. We can use molarity only when we have a way to figure out the molar mass of the solute. Therefore, the use of molar concentration is limited to situations where the solute is a pure substance, like table sugar or table salt. In cases like chocolate syrup dissolved in milk, it's more common to use a concentration unit such as mass percent. Mass percent is the mass of chocolate syrup divided by the mass of milk and the chocolate syrup together times 100%. When we figure out percent by mass, the composition of syrup is not important, only its mass is, and that mass is easily measured by balance in the lab. Living cells use semi-permeable membranes to control the flow of substance through the organism. We model this process with a U-shaped tube containing 2 solutions separated by such a barrier. Suppose this system represents the membrane surrounding the cell. Then, for example, one side of the barrier represents the inside of the cell, and the other side of the barrier represents the outside of the cell, as shown in Figure A. This barrier is a semi-permeable membrane that limits the passage of certain molecules and ions from one side to the other. Membranes can be manufactured, like the one in Figure A, or they can be natural, as cell membranes. Hydrated ions are surrounded by water molecules, and this makes them very bulky. In fact, hydrated ions are too large to pass through this semi-permeable membrane. But water molecules traveling solo, without ions, can pass through the membrane. The movements of those water molecules is governed by the equilibrium principle. Initially, conditions in the tube are unbalanced. The left arm is at lower concentration that contains water plus only a few ions, and the right arm is at higher concentration that contains water plus many ions, represented by the orange dots in Figure A. Note that the water levels are equal. Over time, the system moves away from the initial unbalanced condition and towards equilibrium, which is reached when the ion concentration is the same in the 2 arms. Because only water molecules can cross the membrane, equilibrium is attained by water molecules moving across the membrane from left to right. When they do that, they dilute the solution in the right arm until the ion concentration there is the same as in the left arm. Water molecules move across a semi-permeable membrane from a region of low ion concentration to a region of higher ion concentration by a process called osmosis. Osmosis moves the concentrations of substance on the 2 sides of the membrane towards equilibrium. Osmosis attempts to equalize the concentrations of ions on the inside and outside of a cell. Figure A shows a red blood cell under various osmotic conditions. Initially, the concentration of ions inside is greater than the concentration of ions outside. In this case, water travels from outside to inside, and the cell swells. It is possible for a cell to burst under these conditions. Figure B shows the opposite situation. The initial concentration of ions inside is lower than the concentration of ion outside. In this case, water travels from inside to outside, and a shrinking dehydrated cell is left behind. For comparison, Figure C shows a cell with equal ion concentrations on each side of the cell membrane. Tomato plants do best when the salt concentration in soil is 4 millimole. At higher salt concentrations, the cells shrink because water exits the cells and goes into the soil where the salt concentration is higher. Genetically engineered tomato plants tolerate soil salt concentrations up to 200 millimolar. Question 1. What is the common name for compounds that packed together into crystal lattice structures? A. Bases. B. Acids. C. Salts. D. Molecules. Please pause your video here. The correct answer is C. Salts. In chemistry, a salt is a chemical compound consisting of an ionic assembly of positively charged cations and negatively charged anions, which result in a compound with no net electric charge. The vast majority of salts packed into robust crystalline lattice, like sodium chloride, the table salt. They melt only at very high temperatures. Question 2. Select the ionic compound that contains a polyatomic ion. A. Sodium nitrate. B. Sodium chloride. C. Sodium oxide. D. Sodium nitrite. Please pause your video here. The correct answer is A. NaNO3, sodium nitrate. A polyatomic ion is an ion that contains more than one atom. In choice B, C, and D, there's only one atom in the anion, as chloride, oxide, and nitrite. But for choice A, is nitrate, is NO3 minus, so it is a polyatomic ion. Question 3. What is the name of CH3PO4 twice? A. Tricalcium diphosphide. B. Calcium phosphide. C. Tricalcium diphosphate. D. Calcium phosphate. Please pause your video here. The correct answer is D. Calcium phosphate. You first name the cation calcium plus the polyatomic anion phosphate. You do not have to consider the subscripts 3 after the calcium and 2 after the phosphate ion. Question 4. What is the chemical formula of aluminum hydroxide? A. AlOH. B. AlOH 3 times. C. Al3OH. D. Al3OH 3 times. Please pause your video here. The correct answer is B. AlOH 3 times. We know that Al, aluminum, is a 3 plus charge, and the hydroxide from your polyatomic ion list is OH with a -1 charge. In order to make charge balanced, you need to have 3 of the OH to give you a -3 total on the anion side. Therefore, your formula is going to be AlOH. You need 3 of these. Question 5. What happens when sodium chloride dissolves in water? A. The partially negative hydrogen atoms are attracted to the anion, and the partial positive oxygen atoms is attracted to the cation. B. The partially negative hydrogen atoms are attracted to the cation, and the partial positive oxygen atom is attracted to the anion. C. The partially positive hydrogen atoms are attracted to the anion, and the partial negative oxygen atoms is attracted to the cation. D. The partially positive hydrogen atoms are attracted to the cation, and the partial negative oxygen atom is attracted to the anion. Please pause your video here. The correct answer is C. The partially positive hydrogen atoms are attracted to the N ion, and the partially negative oxygen atom is attracted to the cation. Please refer back to the figure on slide number 9 for information. Question 6. What equation represents the hydration process of magnesium chloride dissolving in water? The choices are given as following. Please pause your video here. The correct answer is A. As you notice that magnesium chloride has a formula of MgCl2 because chloride is -1 charge and magnesium is +2 charge. You need to have 2 chloride to balance the charge from the magnesium. Therefore, you can rule out choice B and choice D. And then, as magnesium chloride dissociates to make 1 magnesium ion and 2 chloride ions, because each formula unit of magnesium chloride contains 2 chloride ions. Therefore, the correct answer is A. Question 7. What is the correct identification of the following substance? Sodium ion, fluoride ion, nitrogen, and water. A. Sodium ion is an anion. Fluoride ion is a cation. Nitrogen is the nonpolar molecule, and water is a polar molecule. B. Sodium ion is a cation. Fluoride ion is an anion. Nitrogen is a nonpolar molecule, and water is a polar molecule. C. Sodium ion is an anion. Fluoride ion is a cation. Nitrogen is a polar molecule, and water is a nonpolar molecule. D. Sodium ion is a cation. Fluoride ion is an anion. Nitrogen is the polar molecule, and water is a nonpolar molecule. Please pause your video here. The correct answer is B. Sodium ion is a cation. Fluoride ion is an anion. Nitrogen is a nonpolar molecule and water is a polar molecule. Recall that cation is a positively charged ion and anion is negatively charged ion. Therefore, sodium plus is a cation and F minus is an anion. That limits your answer to choice B and D. And we also learned that water is a polar molecule from chapter 8. So that further narrowed down to choice B. Nitrogen, N2, is a diatomic molecule. A diatomic molecule has the same electronegativity value. Therefore, it is considered a nonpolar molecule. Question 8. What two processes are occurring at the same rate when a saturated salt solution is in dynamic equilibrium? A. Freezing and condensation. B. Freezing and precipitation. C. Dissolving and condensation. D. Dissolving and precipitation. Please pause your video here. The correct answer is D. Dissolving and precipitation. Once a solution is saturated, there is still movement in the solution at the molecular level. Dissolved ions can be reformed into the salt or precipitated out of the solution. At the same time, other ions can be taken from the solid form and hydrated. Question 9. What is the molarity of a 2.00 liter solution that contains 29.22 grams of sodium chloride? A. 0.250 molar sodium chloride. B. 1.00 molar sodium chloride. C. 0.0684 molar sodium chloride. D. 14.6 molar sodium chloride. Please pause your video here. The correct answer is A. 0.250 molar sodium chloride. To work this problem out, we first want to take the 29.22 grams of sodium chloride and convert it into the number of moles by using the molar mass of sodium chloride, which is 58.44 grams per mole. from the definition of molarity is moles of the solute over liters of the solution. Therefore, what we have here is the moles of the solute. We're going to divide 2.00 liters of the solution. That gives you 0.250 molar sodium chloride. Question 10. Which is a barrier, such as a cell membrane, that limits the passage of certain molecules and ions from one side to the other and allows other molecules through? A. Regulating membrane. B. Permeable membrane. C. Semi-permeable membrane. D. U-tube membrane. Please pause your video here. The correct answer is C. Semi-permeable membrane. Please refer back to slide number 23 and 24 for information.